and comparisons with LADEE observations.
All right, thank you. All right, so, oh, thanks. So what motivated this work is we want to understand when spacecraft land on the moon, how does that affect the environment, and especially the exosphere of the moon. And we had the fortuitous opportunity to study this with LADEE because Chang'e-3 landed on the moon on December 14th last year, and LADEE was in orbit and was taking data to measure the constituents of the exhaust plume on that day. So we model that process. We model the initial impingement of the exhaust plumes on the surface and then the subsequent propagation. And today I'm going to present results from water. And using the model and changing parameters in the model, we're trying to constrain how water adsorbs to the surface of the moon and how it thermally accommodates. And these are really important parameters to understand for water migration on the moon and how that may contribute to water in the permanently shadowed regions. So this is the model that I use of the exhaust profile and the landing profile that was provided by Dan Thomas and Ryan Whitley, where Chang'e-3 starts at 15 kilometers altitude and burns mostly in a prograde direction, and then switches down to, retrograde. Well, the exhaust is going in the direction that the spacecraft was going. Then it angles downward, and then it hovers at 100 meters for 100 seconds, and then finally descends to the surface. And we use a width of the exhaust gases coming out of the thrusters of about plus or minus 12 degrees from the thruster axis. And the byproducts of burning MMH are primarily nitrogen, followed by water and carbon monoxide. And interestingly, constituents 1 and 3 here are both mass 28. And the NMS has a very high background at that mass level. So unfortunately, we're not able to detect these primary constituents over that background. However, the background is much lower for water at mass 18. And we expected that Chang'e-3 probably put 450 some kilograms of water into the exosphere. Most of that escapes because it's most of it was coming out tangential and above the escape velocity. But we simulate about 122 kilograms actually come in contact with the surface. So this is how the model shows the distribution of where that water initially impinges on the surface, where if Chang'e-3 is coming up this way and finally lands right there, that water contacts the surface in a swath that's about 450 kilometers long and about 100 kilometers wide. You don't get very high concentrations of water. This 1 to the 10 to the 15 per centimeter squared here, that's about a monolayer. And that only happens within 1 to 2 kilometers of the surface, or of the landing site. But that's where most of the exhaust actually lands due to the hovering and then the descent happening all at that same location. And so if you consider some of the results of studies of water or thermal water desorption, there's material that comes off at low temperatures, which is water that's bound to other water, but the water that's bound to the regolith comes off at higher temperatures. So the initial coating that's going to go down is going to be more bound to the regolith than the higher doses here. So about 38% of the water molecules impinge on a location that has less than a monolayer, and the rest are less strongly bound. So this is the geometry of the situation where the Chang'e-3 landing occurred about here. This white area is the day side of the moon, and then the darker areas are the night side. So this is the pre-dawn area, that's the post-dusk. And LADEE was in a retrograde orbit coming around like that. And the NMS instrument operates for about half of the orbit on any orbit that it was turned on. And when it turns on and it's operating, it slowly warms up the temperature inside the instrument. And as that occurs, water that's stuck in the instrument comes off the walls and is detected by the instrument. But when you very first turn on the NMS, that water is still stuck to the walls, and the counts that you get are from water that's coming into the instrument from outside. So we can use we understand that process pretty well, and we feel confident about the water measurements that are in the first 5 minutes after the instrument gets turned on any given orbit. And during this timing, that happened at this location here, which is about 2,000 kilometers away from the landing site. And the first orbit after the landing, this occurred about 30 minutes, or 25 to 30 minutes after the burn started, and about 15 to 20 minutes after the actual landing was completed. So here are the data, and it's quite a mess. I have data from the 5 minutes after turn on for several orbits before and after the landing. And to make it a little bit easier to see, I have now separated those out, just displaced them on that axis. These first two down here were before the landing, and the rest of these were after the landing. And what we do is we take a, we do a linear fit to the first 2 minutes, and we see where that fit intercepts the axis here. And we use that as our NMS measurement of the native water that's first coming in when you turn it on, and you don't have the contribution from the water coming off the walls. And this is what we get for our water measurements. This is the count rate. This one, these two were before the landing, and these were after the landing. Here is the time of the landing right here. And we convert that from count rate into density by taking into account the instrumental effects. And we normalize for the known time varying background of the instrument. And so we get the first 3 orbits that we have data from after the landing are elevated. This one certainly. These within 3 sigma are consistent with 0, but we do believe that that is water from the Chang'e-3 landing. So I don't know if this will play. So this is my simulation of when you release the water and you have it thermalized with the surface before it goes. So you can see that there was a initial group of water that went out. That's the water that never comes in contact with the ground and just escapes the moon. And this is over 24 hours after the landing, how the water spreads out from the landing site. And let's see. So then let's go to the next movie, please. So that's if the water thermalizes with the surface completely. Now this movie, no, I don't. Is that the right one? We'll see in a sec. Hold on. So the the next movie was if you, yeah, this one is, so if you don't completely thermalize with the surface, the water molecules, they retain a lot more energy because they're really coming out of that exhaust plume fast. And so if the thermalizing with the surface slows them down quite a bit. So if you don't allow them to completely thermalize, what happens is after they hit the surface, they get launched and they go around the planet. And you see this intensification here at the antipodal point. That's just all the water that diverges on contact with the surface. They're on orbits and they pass by that antipodal point and then land on the surface over here and actually come from the other direction. Okay, so now I'm going to go back to the slides. All right. Okay, so here are just the still shots from the times of the LADEE measurements, those first three after the landing. And for the 70% thermalization and the 100% thermalization. And you can see this ring expanding out here. It actually hasn't even quite gotten to LADEE at the time of that first measurement. The time of the second measurement, it's actually coming in from behind LADEE, which is really important for the NMS because the relative velocity of the NMS and the particles is important to whether the NMS actually detects it. And then the third one, it's more it got into the isotropic case. For the 100% thermalization, you get the water spreading out and then diminishing over time. I don't want to press twice just in case. Okay, thanks. All right, there we go. So now we try to account for that relative velocity effect to see which ones of those particles are actually detectable by the NMS. And when you do the 100% accommodation or thermalization case, it's pretty constant over time. But the 70% accommodation case, you have to adjust, reducing the number of particles from what's actually there to what the NMS would detect at those early times. Okay, so putting those model runs together with the data, here are the data down here, and here are the model runs. So what this tells us is you have to have some portion of the water molecules that stick to that surface at early times when they hit the pristine soil, and they aren't available to migrate, because if they were available to migrate, we would have seen much higher signatures. And also, you probably don't have full accommodation of the water thermally with the surface, that the profile shape fits better when you have like a 70% accommodation. If you reduce the thermalization even lower, you end up having most of your particles escape on the first bounce. So, that seems to suggest that you have maybe about a 70% thermal accommodation of water. So, in conclusion, we think about 446 kilograms of water were released into the lunar environment by the Chang'e-3 landing, and about 122 kilograms of that actually came in contact with the surface, and it exceeded a monolayer within about 2 kilometers of the landing site. And the amount of thermalization has a very strong influence, as you can see, on the subsequent propagation of the water after it comes in contact with the surface of the moon. And that's something that we're going to continue to work on to understand that process better. But LADEE definitely should have detected water for the full thermal accommodation cases. And so if water does thermalize completely, you probably have a big sink in terms of that initial absorption with the regolith. So last slide, is our initial question was, how does a spacecraft landing on the moon affect the exosphere? Well, it has a small effect, but it's very temporary. So, thank you.
Great talk. One question? There.
Hi, John Gruner, JSC. That second movie you showed, where you didn't have complete thermalization, you explained one of the brightenings by being on the antipode, but it looked like there was another brightening at the same latitudinal band of the landing site. How do you explain that one?
That one is water that is never comes in contact with the surface. It's the part of the plume that is directed out or up, and it just goes straight over the pole of the moon and out the tail.
All right. Let's wrap it up here and move on. Sorry. Thank you.